So very good morning to all. So today we are going to start unit number 4. Okay. So unit number 4 is going to deal with inverters. So we have seen basic of power electron devices. Then we went for rectifiers. Then we went for converters. So you can see the sequence by which we were traveling. So we were telling about what and all was there in your various types of switching devices we have seen in unit number 1. So among that we come to a conclusion there are two types like current control and voltage control. Then we find out that current control devices are suitable for some type of application and voltage controls are used for some type of application. So in current control, wherever you convert from AC to DC, you can use current control. Wherever you use DC to DC, then you will go for voltage control. Then we have seen that in two separate unit. So second unit was rectifier unit. So you converted AC to DC. So there you can use all current control device. The next chapter was converters, where you use voltage control device. Now we are going into the next topic, which is called inverters today. Okay. And in today's class we will see about single phase and three phase voltage source inverter. Okay. So the syllabus for unit number 4 is single phase and three phase voltage source inverter. That is it is operated both in 120 degree and 180 degree modes of operation. Then we will discuss about what is the voltage output, that is comparison, the harmonic control and all. Then in harmonic control we will go for PWM techniques. So multiple PWM, sine PWM, modified sine PWM, and there is one more PWM technique called as space vector modulation PWM technique. Then we will move on to design of an inverter. So how you are going to design an inverter. Then comes your current source inverter. So till now what was it was voltage source inverter, then current source inverter. Then we will see application. Application is induction heating and design of UPS. So what is inverter is? An inverter is converts direct current power to alternating current at a particular frequency using solid state electronics. This solid state electronics is nothing but your switches, power semiconductor switches. Now why you want to convert DC to AC? See, there are some, like you have batteries. Okay, batteries we will store in DC. Okay, but all the appliances at your home require AC supply. Okay, I think you all know, like tube light, fan, whatever may be, all such loads requires AC supply. Whereas when you store charge in battery will be storing the charge in the form of direct current. Okay, now there comes the requirement for an inverter. I think you all have a UPS at home and inverter at home. There is a difference. UPS is only for computers, inverter is for entire home. So there inverter, what it does, at normal time from the supply you convert it into DC and try to charge the battery. Okay, that conversion of AC to DC was done in unit number 2, and from that DC getting pure DC with help of converters that we dealt with unit number 3, we have charged the battery. Now we are moving into the next part. From the battery again I want to get back AC and use it for our appliances. So there comes the inverter. So role of inverter, I think now you are clear. It is for conversion of DC to AC. DC doesn't have any frequency, AC have a frequency. And when you design an inverter for Indian countries, we go for 50 Hertz. That is all European and Indian country, because we are ruled by Europeans, so we follow their standards. So European standard. There are one more standard which is called American standard. They go for 60 Hertz. Okay, so that is why it is given a particular frequency. So when you design an inverter for European companies, then you have to decide the frequency as 50. If it is American based company, you have to design the inverter for frequency of 60 Hertz. Okay, now let us have some introduction about today's voltage source inverter. What is voltage source inverter? It is also called as VSI. is a device that convert unidirectional voltage waveform into bidirectional voltage waveform. In other words, it converts the converter into voltage from DC to AC. Now you have to be very clear what is called voltage source, then what is called current source. That is, all the power supplies are voltage source except solar panel, because in solar panel we are able to generate DC, but for the variation in sunlight the voltage value will change and the current value remains constant. Again, in case of voltage source inverter, voltage will be constant and current will vary. If it is current source, current will be constant and voltage will vary, that's all. So in voltage source inverter, input side, your voltage is always kept constant, only current varies depends upon the load. Okay, an ideal voltage source inverter keep voltage constant throughout the process. That is what I have told now. Okay, so throughout the process you will say voltage is constant because it is a voltage source inverter. Now construction, we will talk with respect to construction. A VSI usually consists of a DC voltage source, we all know, a transistor for switching purpose, that is nothing but the device, and one large DC link capacitor. This is for the purpose of filtering, input side filtering. So even if you have DC source, then that DC source might have some ripple. If you put a large DC capacitor, that will filter all the component and you will get a pure DC as an input for the inverter. The AC voltage source can be a battery or a dynamo or a solar cell. If you go for solar cell, it will become current source, but we assume that we make it as a voltage source by putting a very large DC link capacitor. This large DC link capacitor is added to the input side to make it as voltage source, which means voltage should not vary. When you put a capacitor, obviously capacitor will charge and discharge. Whenever voltage starts to reduce, capacitor will try to discharge and keep it as voltage as a constant value. When you want to keep current as a constant, you put an inductor in series. When you want voltage constant, you have to put capacitor. All this you get into your mind, students. So whenever they ask, you have to tell. If they ask, see, I am having a voltage source, there are some ripple, how to reduce the ripple, then you have to tell. Whenever you want pure DC, filter person is capacitor, put the capacitance in parallel. If the ripple is more, put a large DC link capacitor. That is what we will say. And if they say current ripple is there, how to reduce the current ripple? Very simple, put a very high value of inductor in series. When you put inductor in series, obviously what will happen? The current gets filtered. Okay, so the transistor are maybe IGBT, BJT, MOSFET or GTO. IGBT and MOSFET are voltage control device. Okay, the VSI can be represented in two topology. Two topology means either single phase or three phase inverter. Usually the inverter at home we are using is three phase inverter because our loads are, some loads are three phase loads, so you can connect, and there are even inverter for single phase also. Okay, usually at your home we will not go for three phase inverter because it is slightly costly. We will go only for single phase inverter because at home there is no three phase load, except in some houses you will have submergible pump for your bore. This submergible pump will be a three phase, or you will use three phase motor load for pumping. Other than that, all are single phase only. Even your fridge, washing machine and all, it is only single phase. Okay, so when you design an inverter for agriculture, obviously you will go for three phase, like three phase, because there will be a three phase induction motor. Each can further classified, and this single phase and three phase can be further classified. That is, when you take a single phase, in single phase we have half bridge and full bridge. In three phase we doesn't have half bridge and full bridge and all, it is only full bridge. Okay, so let us start with the first one is single phase half bridge inverter. From the word itself it is very clear, bridge is only half, there is not full bridge. The working operation principle of half bridge inverter is based on the fact that for half of the time of the period of the output waveform, one thyristor conduct, whereas other half time period another thyristor conduct. If you say full bridge, for each half you will have two thyristor. If it is half bridge, each phase you will have one thyristor. That's all. I repeat, if it is a single phase half bridge, for each cycle you use one thyristor. Positive half cycle one thyristor, negative half cycle one thyristor. If it is full bridge, you will have 2 thyristor for positive half cycle and 2 thyristor for negative half cycle. Okay, so that is the thing. The output frequency of this type of inverter may be controlled by controlling the switch on and switch off time of the thyristor. So if you want 50 Hz, the T on and T off put together should be 1 by 50, which is nothing but 0.02, which is nothing but 20 milliseconds. So one positive half cycle plus one negative half cycle should be completed in 20 milliseconds. Then positive half cycle should be 10 milliseconds and negative half cycle should be 10 milliseconds. So you have to turn on the switch such that you turn on for 0 to 10 positive half switch and 10 to 20 negative half switch. You will get an AC waveform of 50 Hz. Okay, 1 by 50, 1 by 50. See, F is equal to 1 by T. F is the frequency is equal to 1 by T. So if you want T, it is 1 by F. Then it is 1 by 50 Hz I want. So 1 by 50. 1 by 50 is 0.02, which is nothing but 20 milliseconds. 0.02 seconds or 20 milliseconds. So this is the diagram you can see here. See, since I am going for off bridge, I should need 2 sources. At least 2 sources, or 1 source should be divided by 2. Okay. So this is the main drawback in off bridge. In full bridge, you doesn't want to have 2 sources, you can have a single source. So that is the only difference. Student, you can easily remember, when you say off bridge, you want 2 fellow. When it is full bridge, you require only 1. Okay, when you see the operation, you can see here there is this one thyristor and this is another thyristor. Sorry, wrongly mentioned as D1, 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 D1 itself. It is not D1, D1 and all. So okay, this is thyristor T1, this is thyristor T2. Okay, this is thyristor T1, this is thyristor T2. This is diode D1 and this is diode D2. Now we will see the mode of operation. See, when you want positive half cycle in your output, so what you will do, you will turn on this thyristor. See, when you turn on this thyristor, from this source current enters the thyristor path and then current enters the load. So now the direction of current is in this particular direction. Okay, now you see here, when you turn on this thyristor, what will happen? The current from here will enter the load, will come to this switch and then it will close. So you can see when top is operated, current is in this direction. When bottom is operated, current in this direction. Okay, so unidirectional current is converted into bidirectional, which means you have converted DC to AC. Okay, and what is the purpose of this diode D1 and D2 is, it is for freewheeling. When this is turned off, further there should not be any current flow across this device, so diode will take care. That's all. That is the role of the diode. Okay, I will tell you all that. Now you can see here, this is gate pulse for T1, gate pulse for T2. When T1 is turned on, you will have a positive output voltage for the value of Vs by 2. When this gate and when this is turned off, obviously voltage will come to 0. Again, when you turn on T2, you will have the same voltage, but it is in negative direction, minus Vs by 2. So you can see here, you are getting a square waveform, but square is also in the form of AC. So AC square waveform, you can say sine waveform, like that you can say it as AC waveform. Okay, so you are getting AC output from a DC input. If the load is purely resistive, there is no need to put a diode D1 and D2, as the output voltage and current are always in phase. But unfortunately, for load other than purely resistive, the load current will be out in phase with the load voltage. For such case, a diode is connected in anti-parallel and the thyristor will allow the current to flow when the main thyristor is turned off. When these diodes conduct, the energy is fed back to the DC source. Hence, the diode D1, D2 are called as flyback diode. Flyback. You are making the charge to fly back to the source. So that is why we call it as flyback diode. Okay. Are you able to understand? So just I will repeat. If it is purely resistive load, then there is no issue. Load will not divert anything or load will not dissipate anything back. But if the load is inductor, what happens? You are supplying to the load get charged to something, and this charge, if that particular diode switch is not working, then it will reverse flow. This reverse flow, what we are doing, we are putting a diode, getting back the reverse and supplying to the load source. Okay, so you can see here, assume this is inductive load, So what happened, this inductive load from this supply through this semiconductor I were giving to this. So once this switch is off, this fellow has stored some amount of charge that will try to flow across this diode and then come back to source. So it is freewheeling. I am again supplying something to my source. This will take place during the negative off cycle, or let us assume this thyristor is turned on between 0 to 10 millisecond. This diode will work for 10 to 20 milliseconds. Okay. Similarly, if this thyristor is turned on from 10 to 20 milliseconds, this fellow will work from 20 to 30, or you can call it as 0 to 10 milliseconds. Okay. Means you can see here in negative off cycle what happens. The current direction is in this case. So this will try to again charge this inductor. Now when the switch is off and this switch is on, this fellow has to discharge. That discharge will take place via this diode. Okay. So this will be the current path, and whatever is there, it will be fed back to the source. So at a time, initially only this source was transferring to the load, and now this load is transferring. When this load is transferring, the previously charged is transferred to this source. Similarly, when this source is giving supply, what will do? Via this diode, this source get backs. Again, when this source is supplying, via this diode, what is stored will be transferred to this source. So that is the purpose of your diode. Now I think you all clear with off bridge. Let us move on to full bridge rectifier inverter. In a full bridge, single phase full bridge inverter, it is basically a voltage source inverter. Unlike single phase bridge inverter, this inverter does not require two DC supply. Rather, one wire DC input power source is sufficient. The output frequency can be controlled by T on and T off. That is, there is no difference. So you can see now I have taken only one source. Now two sources is not required because now it is a full bridge. Initially only this portion was there. This portion itself was not there. Rather, you add two source here. Now you can see during positive off cycle, this thyristor T1 and thyristor T2 will conduct and it will close. I repeat from the first, you can see Vs, T1, load, T2, then again source. Okay. During negative off cycle, what happens? During negative off cycle, again from the same source, thyristor T3, load, thyristor T4 and change. Now you can see previously this was in this direction, now this was in this direction. So DC is converted into AC. I repeat, during positive off cycle, the current flow was in this direction. During negative, current flow was in this direction. So during negative, what will happen? If this is inductive load, something might have charged, and this charge will flow via this diode and this diode. So D1 and D2. Okay. So initially you will turn on T1, T2, then diode D1, D2 will come into picture, then T3, T4 will come into picture, then D3, D4 will come into picture. I will tell the sequence. Sequence is T1, T2, D1, D2, T3, T4 and D3, D4. This will be in a sequence, it will be repeating. So this is in case of a single phase full bridge inverter. Okay. So gate pulse, similar gate pulse only difference is there you add IG1, IG2 alone. Now IG1, IG2, IG3, IG4. So it is pair. Okay. So this is for IG1, IG2 and this is for IG3, IG4. When this two fellow is operating, you will get it for voltage Vs, and when this two is operating, you same Vs but in negative direction. So unidirectional voltage is converted into bidirectional. Bidirectional is nothing but AC voltage. So with this, your single phase is over. Just we will go for comparison between an off bridge and a full bridge. So it comprises of two thyristor and two freewheeling diode. Here 4 thyristor and 4 flyback diode. Freewheeling diode or flyback diode, both are same. Next is the magnitude of load bar output voltage is half the magnitude of the DC source. So you can see here very clearly, you can see I have written the waveform as, you can see Vs by 2, not Vs. So output voltage will be only half here, whereas when you see full wave, you can see output voltage is still Vs, so twice the value. Main drawback of this inverter is require two DC input supply, where here it is one input supply. The output power of the full bridge inverter is 4 times that of off bridge. So off bridge, what you are getting output power, that will be 4 times here. Okay. Now let us move on to 3-phase voltage source inverter. Okay, in 3-phase voltage source inverter, it consists of 6 transistors T1, T2, T3, T4, T5 and T6, an anti-parallel diode to all the thyristors. So that diodes are D1, D2, D3, D4 and D5 and D6. It is going to supply 3-phase load. Okay, one DC source is more than sufficient. One large DC link capacitor is required just for the case of filtering, but if you are giving from battery, then this DC link capacitor is not required. Thyristor is connected along with the commutation circuit. The 3-phase output like A, B, C, where A is connected across the switch S1 and S4, B is connected across S3 and S6, and C is connected across S5, S2. The ABC are in turn connected to a 3-phase balance load. So you can see the diagram here. So S1, S2, S3, S4, S5, S6. Just one thing I will tell you, when S1 is turned on, next to that is you have to turn on S6, that is previous leg. See, leg 1, leg 2, leg 3. This two put together we call leg 1, this we call it as leg 2, and this we call it as leg 3. The leg before leg 1, what is leg 1 before leg 1 is nothing but leg 3. So whenever you tell about any top switch, the next person is previous leg bottom switch. So this is leg 1 top switch. So what is the device that should go to conduction after S1? Previous leg bottom switch. So previous leg bottom switch is S6. After S6 it will go to second leg top switch. So after second leg top switch, you have to go to previous leg bottom switch. So previous leg is first leg S4, then comes S3, then comes S5. So I will tell the sequence. After S1 it is S6, after S6 is S2, after S2 is S4, after S4 is S3, and finally S5. This is the sequence of firing. I repeat, this is the sequence of firing. So now this is A point, this is B, this is C. So A, B, C is the 3-phase output. That A is connected to the load, B is connected to the load, and C. The common point is called as neutral. When you connect A, B and C, A is from here, this is A, this is B, this is C. So 3-phase voltage source inverter load, it is a what connected? Star connected or delta connected. When you say delta, all the 3 phases terminals should be connected to each other. In star you will have neutral point. So this is how you are going to connect. Now there are 2 modes of operation in case of a 3-phase inverter. One is 180-degree mode, another one is 120-degree mode. In 180 mode, a switch when you turn on, that switch will be in conduction for 180 degree. What is the total degree is 360 degree. So in 360 degree, each will be deferred by an angle of 60 degree firing. So you will fire the first switch after 60 degree. So it will start from 60 degree and goes to 180 degree. And the next switch will be 120 degree. It will start and again it will go for 180 degree. So in 180 degree mode, you can see here. So first switch at 0 I am firing. It will go till 180 because it is 180 degree mode conduction. 180 degree I have told. So first switch will be in 180 degree. Second switch just 60 degree delay. Again it should go for 180. Then third one is 60 plus 60. That is the delay. Then you will start. That will go till 180 degree. Then comes the next is third 60, 60, 60, 360. Then you will start. It will go to 2 pi. And when you come for fifth switch, this portion alone we will cut it and we will show it here. And similarly here till here we will cut it and this portion is shown here because it is just a repetition. Your time scale is not we are not firing just for one cycle, we will continue our firing for n number of times, so only you will get continuous AC voltage, because you will not turn on your inverter for just one cycle and you will not turn off and keep. This inverter should be continuously operated, so this will be in sequence. Once this is completed, all 6 switches is completed, again I will come back to G1. So only thing you should know is, once I turn on the switches is on for 180 degree. So that is called 180 degree mode of thing. See, you can see this is the output voltage. So across AB, then across BC, then across CA. Now the difference between the two is always 120. We all know when between A phase and B phase, what should be the differences? Difference is 120 degree. So now you can see R phase, Y phase, Z phase, R A phase, B phase, C phase. So this is AB, this is BC, this is CA. You can see there is a 60 degree. See here, after this it starts. What is the time taken here is 60, 60, 120. Similarly, after this it starts. This is 120, again one more 120. So this is 240. So this is how we are able to get AC waveform, 3-phase AC waveform. Next comes 120 degree. The only difference is here, when you turn on, you are turning on for a 180 degree. What we will do is, we will turn on only for 120 degree. Okay, so that is called 120. In this mode, conduction, each electron devices is conduction state for 120 degree. It is more suitable for delta connected load, delta connected, not for star connected, result in 6-step type waveform across the phase. First one is for star, second one is for delta. So when they ask for, I want, since my load is star, what should I do? What type of 3-phase inverter I will go? If my load is delta, what type of modes of operation I should go? So that is what 120 and 180. Okay, so depending upon the load only, you will go either for 120 or 180. If the load is delta, you will go for 120. If the load is star, I will go for 180. So here the phase voltage and line voltage are same. So VAB is equal to V minus VABC is also minus V by 2, and that is also minus. So there is no difference between line voltage and phase voltage. Whereas you can see here, for this is for 180 degree. For 180 degree, the load voltage, that is phase voltage and line voltage, are different. So phase voltage is V by 3, 2V by 3 and V by 3, and here it is V minus V and 0. So with this we will stop for our discussion today. Now if you have any doubts, you can ask me.